In week 2, we're going to be looking at the corner point theorem, which is one of the most important results in the course. And basically, it tells you that the solution to a linear programming problem will occur at one of the corners of the feasible region. Now, there are some simple concepts involved in this and some rather subtle ones. So let's just look at the basic setup. So in linear programming, we're looking at an objective function, which is linear in a certain number of decision variables, x1 to xn, and the constants here, c1 to cn, are just some real numbers, could be positive or negative, and the linear programming problem is subject to a number of linear constraints. So they are linear in the decision variables, x1 to xn. The numbers a1 to an and b are just real numbers. And these constraints determine the feasible region, and the corner point theorem says that the solution, which is the maximum or the minimum value of z, whatever is required, that if it exists, it will occur at a corner. And the geometry that's involved here is called convex geometry. And convex geometry is a whole area of mathematics in its own right, and at some universities you would have an entire course devoted to convex geometry. We'll just have a little glimpse at what the basic ideas are. And we need some notions. One of the simplest notions is the notion of a line segment. So this is just what you're used to. The line segment from P to Q is the set of x values of the form P plus T times Q minus P, where T runs from 0 to 1. You notice when T is 0, plug 0 in here, you get x equals P. When you sub in T equals 1, you get P plus Q minus P, and so that's x equals Q. So as T varies from 0 to 1, x varies from P to Q. We have another notion here, which is the notion of a convex set. Set is convex if for all pairs of points P and Q, the line segment for all pairs of points P and Q in your set K, the line segment from P to Q is entirely contained in your set K. So a set is convex if it doesn't have any holes, it doesn't have any dents. Now, a simple, very easy to prove theorem says that half spaces are convex. That's just need to directly see from the definition that this is the case. It's treated in the printed notes. And another simple result is that the intersection of any finite number of convex sets is convex. And again, that's really simple and straightforward. That's treated in the notes. And you put these results together, you get the fundamental fact, that the feasible region of any linear programming problem is convex. What's a little bit more subtle is the concept of a corner point. Q is a corner point of a convex region if the set obtained by eliminating that point is also convex. A convex combination of a certain number of points is just a set of linear combinations that you can write down. So combinations of the form d1k1 up to dmkm, all added together where the d's are constants, and this linear combination is a convex combination if the constants are all non-negative and they sum to 1. And the final key concept is the concept of a convex hull. A convex hull of a set is a set of all convex combinations of points in the set. So here are the three important concepts: corner point, convex combination, and convex hull. And typical questions, like exam questions for instance, would be to see whether a given point is a convex combination of some given points, and given a set A, to determine and perhaps draw that convex hull of that given set. And the basic important results concern the feasible region of a linear programming problem. And one of the little notions we're going to need here is the notion of a bounded set. Remember, a set is bounded if all the points in the set are contained within some fixed distance of the origin. In other words, k doesn't go off to infinity. And we've seen in week 1 that if the feasible region is unbounded, then it could be that there are no solutions to the linear programming problem. And this theorem here in the notes, theorem 2.10, tells you what the situation is for any feasible region of a linear programming problem. It says that there are at most finitely many corner points, and if the feasible region is bounded, then every point in the feasible region is a convex combination of the corner points. In other words, the feasible region is the convex hull of its corner points. Now, this theorem is really quite difficult to prove, well beyond this course. In the printed notes, you'll find in one of the appendices a proof of this theorem in the case where the feasible region can be drawn in the plane. And that's just to give you an idea of what the general proof might be like. And finally, the corner point theorem. The corner point theorem just summarizes all this information. If you've got a linear programming problem and subject to a finite number of linear inequalities, then if the feasible region is bounded, then the optimal solution occurs at one of the corner points. If the feasible region is unbounded, then an optimal solution may not exist. However, if one does exist, and if the feasible region has at least one corner, then the optimal solution is attained at a corner point of the feasible region. So that in all the interesting cases, the corner points are where to look for the solutions. And as we go forward in the coming weeks, we'll look at a systematic way of searching the corner points to find the optimal solutions. And this is called the simplex algorithm. That's the topic we'll commence next week.